and I will just talk about it, and we'll go through this kind of thing. This represents processes. So in this graph, we have 3 processes. This represents the resource. So if you have a resource and maybe it has several like subcomponents that it can kind of share, there are these little circles. So like memory, let's say you can, process can share memory, and there's like, so if we think of this as memory, let's say this memory has like 4 buffers and this one has 4 buffers. And then when it could be whatever you want it to be. I'm just like, and then let's say this one, when it allocates to this process, you have an arrow going from the resource to the process. That means that the process has the resource. If you have an arrow going from the process to the resource, that is a request. So like this is it asking if it can use the resource, but it hasn't been allocated the resource yet. So this one, it's allocated from here to here is just the request, and then resources and processes. So yeah, nothing too crazy. Let's just look at this real quick. So 3 processes sharing 2 resources. They each have 4 identical units. P1 is holding a unit of R1. From this graph, we can see that. P2 has a unit of R1, and P3 has 2 units of R3. So we haven't really talked about this in the other sections, but you can, like, a process can have more than 1 unit of a resource, like it has a bunch of them. Yes?
Well, what about the remaining of the 2 for R1?
They're just not being used. Yep. Good question. And then P1, okay, so if we look at this, we can see if a process is blocked. And when does a process get blocked? We've talked about this in the other sections. Like what's one in relation to resources? When does a process get blocked?
Like if something else is using it?
Yes. So if there's like, yes. So the same thing here. P1 is not blocked on R1 or R2 because it's not asking for something that it can't get. Okay. And then P2, okay, so also we haven't seen before, a process can make multiple requests. Like the process could say, I need 2 units of this resource. And so it would basically block if it doesn't get the 2 units. It's like and it needs to be right now, like at the same time. So that's what's happening here. So P2's blocked because it needs 2 units of R2, and there's only 1 unit of R2 left. And so yeah, and then here they say, so P1 and P3 aren't blocked here because in this one, P3 is asking for a unit of R1, and there's 1 there, so it's going to get it. This is the ask, like this arrow going this way. So eventually it's going to get that resource. But P2's blocked and P1's not blocked. So like if we took a snapshot of this resource allocation graph and I asked you, why is P2 blocked? Why is P2 blocked? What's going on there in this graph?
Because it's used in R1. And there's no more space in R2, right?
Yeah, so it says I need 2 units of R2 and there's only 1. So it's just got to sit there until like another unit's released. And then if I say like, why is P3 not blocked? What's going on there?
Because there's place to run it in R1.
Yeah, exactly. So there's it's asking for a resource and there's going to be 1. And it's got the resources from R2 it needs. And the same for P1. P1's not asking for anything and it's got the resources it needs. So it's not. So that's that graph. So we can kind of see what's going on with the graph, like like what's in this. It's a snapshot of the system. And this snapshot of the system is called a state. We're going to see that as we're going to have like different states you can look at. Okay. These we're going to skip this. It doesn't help. It's a bad activity, so you can do it, but it's not helpful. Okay. This is just talking about deadlocks that can happen. So we are just going to kind of look at this activity and also skip this one because this is also bad activity. So yeah. So when you have two processes or more, or two resources or more, you can have a deadlock. So deadlock involves at least two and at least two resources. If you have less than that, you're not going to have a deadlock. Where each process holds a resource and is blocked indefinitely on another resource. And so what we're going to talk about in like at the bottom of this section is how to find a deadlock in a system. And so this just shows how a deadlock can happen. So here we have some processes. We have three processes and three resources. And in this one, from this graph, like here, P1, so what's happening here? I'll ask you guys, look at this graph here. On the left, what's going on here? What's P1, P2, and P3 doing?
So
on the left, before the arrow, yeah.
I mean, everything used twice.
P1's asking for both resources P2 is and P3 is.
Yeah. And
right.
It's not like it's going from P1 to 3, not from the R. Like on the
yes.
right side, it's going back.
Yeah, so this is the request. So if it goes from P1 to the resource, that means it's a request. But the resource hasn't decided what it's going to allocate to yet. So now P1 is going to, so these arrows basically mean R1 gave the resource to P1, R2 to P2, and R3 to P3. Using some kind of algorithm or first come, first serve or something like that. Okay, so in this case, there's deadlock because now P1 decides it also next is going to need R3, and P3 needs R2, and P2 needs R1, and they're all blocked. So everything's blocked. Okay, and it doesn't matter. This whole thing here is saying deadlock is regardless of order of the second request. So it does not matter the order. This could be any order. Okay, and we're not going to go through this. You can, but this is just showing ways that deadlock couldn't occur. Which is like, okay, there's lots of ways deadlock. This is the one way deadlock could occur, and there's like a bunch of ways deadlock couldn't occur. Yeah, so we're not going to do that. Okay, deadlock is possible, and we're going to do more examples. So deadlock is possible when the number of processes is greater than 1, regardless of number of resources. The number of resources is greater than 1, regardless of processes. Or the number of processes and the number of resources are both greater than 1.
Both greater than
yeah. That's true. Okay. We're not doing this. Yeah, we're not doing it. Okay. And this is all, like, I'd say skip this one, skip this, so yeah, you're fine. Okay. State transitions. So we have this resource allocation graph. There's three things that are basically happening that we saw. You have a resource request. You have that's when you ask, when the process asked. You have an acquisition. That's when, the resource is given. And then you have a release. So that's when the process does not need the resource anymore. So these are the three things in that graph. And this is just basically the details. So you do the request. That only happens when a process has no outstanding request. And the number of requests plus the number of allocation must not exceed the total number of units. So if this happens, we have a block happens. So this is just basically saying you can have a request, but if, there's not enough units of the resource, then you're going to be blocked on the resource. That's all this is. Let's see. Resource acquisition. It only happens when you have a certain number of free units. So if there's like R requests, you have to have R free units. These are kind of common sense things. So let's look at this. So what this is called a state transition graph. And for each one you have, so basically each snapshot of the resource allocation graph is called a state. So this is a state. In this one, what's going on here? What's happening in this state?
P2 has
Yeah.
one of R's resources.
Yes. Here we have like just the description down here. And then now the state can go to the next one. So in this one, we're saying, okay, R is going to request 3 of R requested 3 units by P1. So that's going to be the next state. So we'll see that. So P1 asks for 3 units of R. P2 still has its thing because we haven't done anything with there. That's the new state. And P1 is blocked because we don't have enough like units. Okay. Then the next state is P2 releases a unit. So in this one, P1 becomes unblocked because P2 released this, and so now P2
back
can
to
go.
the R at all?
Sorry?
It doesn't go back from P2 to R.
That would be a request.
Yeah, that's a request. So release is just basically like the arrow goes away. Yeah. And so at that point, P1's not blocked. So it's pretty straightforward stuff. And now, because P1 is not blocked, it can now acquire, so these arrows go this way, they change direction, right? Because now the resource is going to give P3 all of the units. They're saying alternately P2 could request, R, each of which would take the system into a different state. So there's other things that could happen. This is what happened because of just how the system's running. And then in this state, they just say there's all these things that could happen. In this case, our P1 is going to release 2 of its units. And so that's what this graph looks like. And so this is a state transition graph. It's just like you have, this is what's going, and then this happens, and, it just looks like this. Very straightforward. And we've kind of like talked about all of this in the other sections as far as like scheduling and stuff. So we know about like resource, you request from a resource, it gives you like access or it doesn't, and being blocked and stuff like that. So it's pretty straight. Yeah. Are we good? Yeah. Okay. So that's that. These are kind of weird questions, as the book likes to be kind of weird. So, but let's just look at this. So bring this up on your computer because we're going to answer these questions, and you'll need this one. And I'm going to like kind of go down to here.
Like the all of them?
Yeah. Okay. In state S0 of the above graph, what could P1 do? Can it release R? Can it release a resource? Or no, it doesn't have a resource to release. So P2 could request 3 units, or it would request 1. It can. This is weird because it could literally request 3 if it wanted to. It should say
what would work.
What would not be blocked, right? Because it's going to be blocked. P2 is going to be blocked if it requests 3. So this is a little weird.
It says P2 is already holding 1 unit.
Yeah.
Would violate the rule of the sum of requesting.
Yeah, what you mean is the rule is like if you don't want to be blocked, this is what you do. So
Because they literally do that in state 2
yeah, so it's
or
weird.
state 1.
So like if I give this on a test, I would be like, what would be allowable without being blocked? Like it'll be very clear.
There was a lot of trick questions.
No, I try never to give trick. Well, actually, I was being a little tricky with that first. That trap question. I'll go back to that one, but generally I'm not tricky. I'm not going to be tricky. I'm so tricky.
She wants us to get that false hope.
I'm moving away from true-false questions because this just gives me a headache, so I'm not doing those. Anyway. And I also hate Mountain Dew, and that's all that there was in the vending machine, so.
Do you notice there's like
But I needed
5
caffeine.
selections in that machine that are just there because you can't get them. It says they're out.
Yeah. It made me very sad.
I want that water bottle so
Did you
bad.
figure it out?
And the other machine
Yeah.
is only non-caffeinated things.
I did.
Or wait, or it's, so I'm like, that does me no good. I need straight up caffeine. This is going to kill me, though, because I'm too old for Mountain Dew. You can't be past 30 and drink Mountain Dew. Okay. In state S1, so let's look at state S1. Okay. Okay, we're going to go to 3. Okay, here's state S1. P1 could release R3. It can't release because it doesn't have them. It's requesting. P1 could acquire. It could because there's 2. So I guess that's the one. P2 could request.
It's P2.
Um, It would be this one. Oh, wait. What? Why is it saying this?
It's the next P2 could.
Oh, because it has. Oh. It could later. Okay. P2 is holding a unit and can request up to 2 more. Okay.
Okay, state 2.
State 2. Let's go to state 2. Okay. So P1 is asking for all 3 units. P1 could release. No, it doesn't have them yet. Could it acquire one, or would it? P1 could acquire. If it's asking for 3, then it has to get all 3. Okay, so if we say this one, it has 3 outstanding requests. The way these graphs work is if you ask for like 2 things, you can't get like partial things. This one, let me go back to this. I want to make sure. Yeah, that was, sorry. So yeah, if P1's asking for 3 things, it has to be given all 3. So that's the thing there. And then in 2, also, it can't just get 1, it has to get all 3. So that's what's going on in the second and third question. And then state S3, so let's bring that up. Okay, S3. Okay, so in S3, P1 has been granted all 3 resources. So let's see what could happen. P1 could request another resource. No, it can't do that. P2 could request R of 3. It can, it will be blocked. I mean, is that what are they asking? P2 could acquire R of 1. It can't do that.
3, what?
This is so weird. They're kind of like invalidating what they said earlier. Yeah. Quest blocked. That's so weird. Okay. P2 is holding a unit and can request up to 2 more. Okay. So we looked at the resource allocation graph, and we have the states. So now we have this really fun graph here. This is just a giant state graph. And we can look at this and kind of see this graph in a minute. We'll see the whole thing. We can see from the graph where you could be deadlocked and which are safe states. A safe state is basically if no sequence of state transitions exists that would lead to deadlock. So let's just look at this. See the state 21 here? These are all states, and I'm going to explain this more. There is a way out of this state. Like you can go from here to here. You can go like down. Yeah, you could go basically across or down. So this is called a safe state. In this state, you can't reach a deadlock in this state. Okay? This state is a deadlock state. And we're going to actually be able to draw out the resource allocation graph in a second, too, from this state. But this state is a deadlock. Why do we think this is a deadlock state? Based on what I said earlier.
There's no way to leave.
There's no way to leave it. Okay? And so we can actually draw this state diagram in this way, and it's going to take you through it. Okay. So, oh wait, oh, it's down here at the bottom. Let me see if I can make this smaller so we can get it on one screen. Okay. So, we have this state. There's no resources allocated. This is called state 0. These numbers are completely arbitrary. They just have to be different from each other. And this is basically what's happening in the system. When P2 is not using any resources, P1 can request, acquire, and release R and 1, 2 in a certain order. And this is the order. And so this has to be told to you. So it can request R1 and then acquire R1. And then it can request R2. And then it has to release R1. Then it can acquire R2, release R2, and then it can release. So this is what it's doing just over and over. Asking for R1, getting it, then it can release it, and then it can request R2, acquire R2, and do a release. Over and over. So this is P1. This is behavior. If it was by itself, if P2 was not around, okay, and it just had the resources to itself. So that's what it says here. When P2 is not using any resources, P1 can repeatedly request, acquire, and release both R1 and R2 in this order. And then it's going to show it too. Do they show it? Yes, they don't. It's kind of sad. Okay. They do. Okay. Okay. And so it requests R1, then gets that, gets R2, then releases R1, then releases R2. Just what they're showing here. Like that. Okay, so that's P1's behavior without P2. So when you have a state transition graph, what you do is on one axis, like we're only going to do 2 processes because it gets super complicated. You draw what one process would do without the other process, like its behavior. So this is P1's behavior. This is, what would this be? If this is P1's behavior and we have 2 processes, what's this? I mean, like, what does this represent? This vertical. It's not P1 and there's 2 processes. P2, yeah. P2s. Okay, so this is the state transition for P1 by itself. It's saying, and this is also told to you, this is just how it works. It's like, this is how P1 would work if P2 is not around. So this is not something you know. It's like, you know, specified. So P1 always requests R1, gets R1, then asks for R2, then gets R2, then releases R2, then releases R1. And then the behavior for P2 is P2 requests R2, it's the opposite. So its behavior is it asks for R2, gets it, asks for R1, gets it, then releases R1 and releases R2. So it's kind of it's the opposite from P2. So the question is, with these processes acting this way independently, together, when it's doing all these requests and, you know, releases, are we going to ever be in a deadlock state? And so you just basically have to keep drawing this graph out, which is like not super complicated, but it looks complicated, but it's not so bad. It's just time consuming. So, this is the graph. So if you just look here, this is like if, okay, all of these arrows here are all for P2 requesting R2. And all of these arrows are basically like, this is request R1 acquire, request R2 acquire for P1. They just don't write everything because it would be really hard to see all the arrows and stuff. So like here, like this is saying that we're in this state when, let's see, P1 has requested R1, because we've got this, and when P2 has requested R2. This is the state. Is this state a deadlock state? Yes or no?
No.
It isn't, right? Because if there's a way out of the state in our graph, then we're no. So this is called a safe state. Let's see. Is this a deadlock state? No, it is not a deadlock state. How do we get to this state? Why is it not a deadlock state? What is letting it help? There's one thing that's keeping it from being a deadlock state.
P2.
That's always a good guess. This arrow. So there's a way out of this state. Okay, so we can go to this state. So a deadlock is basically when you can't leave the state. You're like stuck there. So if there's a way from one state to another, it's not deadlock. So there's a way if we release R2, if P1 releases R2, then we go back to this state. Okay, so this is not a deadlock state. You can see what the behavior is to get to the state by like tracing it. So like to get to this state, it was like P1 requested R1. Let's say if we went from here, requested R1, acquired it, requested R2, acquired it. And then P2 also requested R2. So we could draw this out too. Like we could, for each of these, you have a little resource allocation graph that you could draw. Okay. Is this a deadlock state? Is S33 a deadlock state? Yes. Because we can't, there's no way out of this state. So that's not good. Okay. So that's what a state allocation graph is. It's basically you draw it out, or it's kind of created by the system to see, like if we have processes and resources, if there's any way that deadlock can occur. Here they're just talking about, I've kind of said this, but in this state, P2 is holding R2 and R1 because it's requested and acquired. We know that because of this. And P1 hasn't done anything because we haven't, it's at this part. Okay. Let's look at another. Okay. If P1 now requests R1, then P1 becomes blocked in state S14 because R1 is already held by P2 and cannot be acquired. So there's no way out of this. So it's a block state, but it is not a deadlock state because there's once P2 releases, which one is this? Releases R1, then P1 will have access to that state. Okay. So what else do we want to say? Okay, so that is a good point. So if there's no transition out like one direction, you can say it's blocked by, so like there's no way out this way, so it's blocked by P1 is blocked, but it's P2 was going to release, but P2's not because there's a transition out this way. Let's find another one. Is there another one? This one's blocked. This one's deadlocked. One that's like blocked. This is blocked on P1 because there's no way, there's nothing going this way because P1's going this way, P2's going this way. 23 and 33 are blocked. Yeah. Let's see. 23. Where's 23?
Next to the deadlock one.
Yeah. This one's blocked by P2's blocked because there's no way it's not going down. So this is kind of cool. So this is deadlocked, right? Because it's not going across or down. There's no way out. So P1 and P2 are both blocked. If they're both blocked, if all your processes are blocked, that's deadlock. So that's kind of nice too. So you can look at this graph and kind of see like what behavior leads to what, what behavior leads to blocks, resource blocks, and what behavior leads to deadlocks. Okay, so let's just answer these questions. They're just basic questions about the state graph. So operation by process 1 corresponds to what in the transition graph? Horizontal edges, downward pointing edges, or upward pointing edges?
Horizontal edges.
Yep. So it's going across. In which states is P1 blocked? Okay, so let's look for that. And I think we've already.
Isn't it was blocked in 33, right? It's 33.
Yeah, but then they have the one with 32 and 14, so we have to check on that. That's good though. So it's definitely blocked in 33 because that's a deadlock. What's the other one?
32 and 14.
Okay, 32, it's blocked. And what about 14? I have such a hard time finding the numbers here.
Bottom, the yellow one.
It's blocked there too. So yeah, true. So all those are blocked. Okay. Which states are safe states? That's when basically.
Early none.
So what is a safe state?
A safe state. There's no sequence of state transitions exists that would lead from S to a deadlocked state. So basically, I thought. Now I need to make sure that it is basically not a deadlock state. I thought everything that's not deadlock is a state, is a safe.
Oh, it's everything except 32 and 23.
Is 23 a deadlock state?
No. Oh, never mind. I thought it was no sequence of state transitions exists that would lead from your safe state to a deadlock state. So the only states that will lead to
that's true.
Are 23 and
You're
32.
Right.
Didn't like it though.
Oh.
Okay.
So if you have a deadlock in the graph anywhere, nothing is safe. The whole graph is unsafe. That's that. If you don't have a deadlock anywhere in the graph, they're all safe. Or if there's a deadlock, let's say this incorrectly. Like, there could be, I'm assuming, you could have, that would be weird though. Yeah, we'll just use that definition. That's actually a good definition. If no sequence of state transition exists. So, yeah, these are all basically connected to each other. So, they all lead to the deadlock. Okay. State 22. So, this one's just making sure we can read this graph. So, what's happening in state 22? Let's line that state.
State 22.
P1 has R1.
Yes, P1 has R1, and then what else?
P2 has R2.
Yeah, so let's make sure we can.
Asking, or no, it's not.
Okay, and then let's go find 31 and see what's happening with 31. Is there a 31? Where is it?
P1 has R1 and
Yeah.
is requesting R2.
Okay, and then.
And P2 is requesting R2.
Okay, so let's remember that.
31.
This one, right? Yeah. Okay. So we can read the graph, and we have verified the safe state. Okay. Let's do some of these exercises. I just made them like visible. It's just like more of the same thing, and it's good to practice. Okay. So before we look at the solution. So which processes are blocked looking at this resource allocation graph? Is P1 blocked? Let's start with that.
P1 blocked. No.
No, it's not blocked. Because it's asking for R2, and there's 2 units there. so it can get one of them.
P2 is black because it's asking for R2 and there's 2.
Yeah.
P3 would be black because it's asking for R2 and both resources would be.
So P3.
Well,
P3 is blocked because it's asking for R3 and that one's being used.
yeah, it's not blocked yet. It will. We don't know if it's blocked. It's kind of
You
a
don't
weird
read it
thing.
left or right. I don't know.
We can't say for sure it's blocked. It might be blocked. It's according to what
R2,
happens
like,
next.
hasn't been assigned to anything yet, so
Yeah.
it's not going to block anything yet.
Yeah, so it's not blocked yet.
But R3 is assigned to P4, so that will block.
Yeah, so P3 is definitely blocked.
And then R4 is assigned to P3, so P4 is blocked.
Yes.
Yes.
Yay, good. Okay. Which processes are deadlocked?
All of them.
No.
Okay.
P3, P4.
Yeah.
So what did you say?
P3, P4.
Yes, that's right.
Because there's like.
So that came out kind of like, what did you say? You didn't say anything wrong. It was more of curiosity. It wasn't like you said a bad thing. That's actually correct.
What'd you say?
That's how I talk to my kids. What did you say? But I didn't mean it. I didn't mean for it to come out that way. Okay, P3 and P4 are both in deadlock.
Is that because there's like this circle?
Yeah, that's what I actually look for, and that makes it easy. Is that if you see this circle there, then that's a deadlock. So that's the way to look for that. There's no way out of this behavior, basically. Like this isn't a deadlock because
It's like countries combating climate change. They all want everyone else to do it.
yeah, and they're all deadlocked. No, yeah.
Yes.
Yes!
Sure you can.
What?
Yes. Can I torrent a school's network friend and say yes?
Can you what? The school's network?
Torrent.
Oh, can you torrent on? What do you mean, like make a torrent from it? Like
Yeah,
via?
like download something. I'm sure
You sure? I'm sure you could, but you'll get an email from because I'm sure because like the HBO and all those they like track all that. Huh? You're not doing anything with.
I have HBO. I don't need
So you don't need that. It's according to what you
It's
torrent.
just as long as the school doesn't
Helping
get an
you with
email
illegal.
saying, "Hey, cease and desist," bullshit, right?
They probably won't do anything because that's the problem. It's like from the things you have to pay for, like HBO.
Stuff I want to torrent. Is
Unless you're torrenting a lot of stuff.
I'm just downloading a private server for now.
If you're downloading a lot of stuff, they're gonna
I
notice.
just don't want you. I just don't want my internet privilege taken away.
That's why you ask somebody's ID.
Yeah, we.
Log into my computer.
Any of relatives, graduate from Central. It's there.
Okay, let's see. Okay, now let's look at this state. Okay, well, this is fun. So the state transition diagram in the activity titled that we just looked at represents the behavior of two processes. Modify the diagram so that each process acquires the second resource without releasing the first. This is a bit much because you're going to have to draw the whole thing. So what they've done here acquires the second resources without releasing the first. So all they've done is taken out this arrow here and then releases both at the same time. So here they've acquired both and then they're releasing them both at the same time. So this would just say like release P1, like release R1 and R2. So it would be like,
Okay.
yeah, so that's
Doesn't
weird.
work.
Yeah, that's the solution. And so we modify that diagram. Modify the diagram so that P1 only needs resource 2. So it's not asking for resource 1. So that gets rid of this whole part right here. They should have put the words on there too. That would help. So basically this is just going to be saying ask for resource 1 and acquire resource 2. So we just got rid of like half the graph, or of like this part of the graph.
So when they say for the safe state thing,
Mhm.
is it either going to be they're all safe states or none of them are safe states?
Well, that's what I'm not sure of because I don't know if like you can have a graph where it's not fully connected. right? Because if it's fully connected, you can always. So if it's fully connected, yes. But if it's not, but I'm not going to ask
Like
that if
having
it's not in the
an island
material.
off somewhere.
Yeah, but I don't know if that's possible. So I'm not sure. Does either modification eliminate the possibility of deadlock? Okay, so looking at these two graphs, okay, is there a deadlock happening in this graph? Yes. Which state is in deadlock?
Same one.
Yeah, it's the same one.
It didn't help.
It didn't
It
help.
makes worse.
And then, is there deadlock in this state graph?
I don't think so.
I don't think so. We can leave here. Is there anything else you can leave? Yeah, there's no. So that helps. So yes. So the first graph contains a deadlock at S33. The second graph is deadlock free. That's cool. Okay. Now we've got these two these process interactions. So P1 request R1, request R2, then releases R1, releases R2, request R2, request R1, release R2, release R1. So let's see what we draw. So we're assuming that after they request, they acquire. So here we have P1, request, it acquires, request, acquire, and then releases R1. And then here we have request. It's kind of the same thing, but going down. Yeah.
Are we going to have to create any of these?
No, you're not going to. You're just going to have to read them. Like, it'll just be like, what led to this state? What behavior led to this state? So you say P1 did this and P2 did this. Or it'll be like, which is the deadlock state?
And there could be like more than one path that could get you there.
Yeah. Like, what's a deadlock state? What states are blocked? Like, which are the states, or is this state blocked on P1?
Mm-hmm.
So, like, you would just have to make sure there's, like, for P1 it's going across, so if there's no arrow going this way. For P2 it's going down if there's no arrow going to this. So nothing crazy. It's just reading the graph. You're not going to have to draw it. It's super time intensive to draw one of these graphs. Okay. Here, this is interesting. So this I could ask. So for each state, draw the resource allocation graph. Okay, so this is basically just making sure you understand how to read a state diagram. So for, like they say state 10. So P1 has requested R1. So that's what a request looks like, right? Mm-hmm. So you just can draw that. So this is testing. Do you know how to draw a resource allocation diagram, and do you know how to read a state diagram? Like S11, P1 has requested and P2 has requested. So that's what this looks like. So here they have you draw S33, which is a deadlock state, and that's what it looks like. And so it's also just another way to see what that it's verified it's a deadlock state. R1's requested P1. R1's been allocated P1. No, wait, my brain. R1's requested P1. R2 has been allocated P1. Right? Am I opposite?
Yeah.
Our
resources.
When the resource goes, it means you're given, yeah?
Yep.
Resource 1 has been given to P1. P1 has requested R2. P2 has been allocated to R2. And R1 process 2 is asking for R1. So that's deadlock.
R2 is allocated to P2.
Did I say that or no?
You
I confused
You said P2 is allocated to R2.
Sorry. Sorry. Oh, yes, the opposite. Brain. Okay. So, that's the main thing. Let's see. This one I'm not going to ask you to do, but this is just a state diagram. So and then here's another one. Yeah.
It seems like these would get really complicated really fast.
Yes.
Because as soon as you needed a third resource,
it'd be really crazy.
It'd be like a three-dimensional.
Yeah. So a computer has to do.
Right. So that's what I was.
Yeah.
The next question was, do you just create one of these like as a computer model to figure out if
Yes.
if there is any deadlocks in your system?
Yes, you do. Because there's lots of processes going on, so there's no way to like. So yes, just like a model, and the computer like does this and kind of figures out. Okay, so let's just make sure this is just one more thing to make sure we know like about, looking for block states. So, so which states are blocked? So let's look for the blocked ones and then we do the deadlock ones. So, blocked, there's a way out. This is blocked by P1, it's blocked. It's 12.
This is,
Mm-hmm. Isn't it?
this is the modified graph.
Yeah. Are we supposed to? Yeah, so this is a graph that they modified, so it's like a new graph. So we're blocked on from P1 by 12, 13, 14, and 15.
And then 21, 31,
Make sure.
41, 51.
Yeah, for P2. And then deadlocked.
None.
Yeah, I don't see anything. See if we're correct. Yeah, so good. Okay, questions. So it's just a lot of vocab. Making sure you can read some graphs. Nothing super crazy. Okay. And I won't ask you to create one, but I'll just ask you to read them. Make sure you can read them. You will have to draw a resource allocation. No, I'm not going to ask you to draw a resource allocation because I can on a Blackboard test, but I'll maybe have you like pick one or something. Like say some behavior and be like, which of these? Multiple choice or something like that.
Use your webcam to show your drawing.
Take a picture with your phone, upload it to your computer, and then I'm not going to make you do that. So, okay, what time is it? For one.
I opened it up and snipped the wire so I don't have to put a piece of tape over it.
Okay.
You're working.
Okay, this is a good place to stop. Then we're gonna kind of go. We're gonna go through 5.2.
The test
Half
only
of
goes up to 5.1, right?
Well, I had it for 5.2. So, but I don't think we're gonna make it through the whole thing. So, like some of 5.2 maybe. So yeah. Okay.
Must have.
Okay. I'll be right back. It's recording.
I saw I saw
Thank you.
the door open. So I saw Eichel's door open. So I'm not looking.
Stupid, stupid. Oh.
Okay. We'll wait for a minute or two. So I'm getting a passport for the baby because, yeah. So both parents have to go to get the passport, and my husband left the country, and so now I have to get a signed, notarized document.
That's so weird. Both princesses too.
Yeah, because they're afraid one will take the other. Like, they're afraid one would go and get the passport and take the kid, and then the other wouldn't know.
Mm.
So, which is not happening in this situation. But
It's
they
so
don't know.
weird. In
So I have to get a
Mongolia, I
notarized
went alone.
document. Huh?
In Mongolia, I went alone to get it. Yeah, I totally went alone.
Really?
Because my dad is like, yeah,
Yeah.
showed me like where to go.
How old were you?
I was like 16.
Maybe it's like yeah.
Yeah. I guess it's just country thing.
Yeah. In Morocco, it takes forever. The government, there's like, but it's pretty slow here too. So I guess it's just bureaucracy.
Yeah.
But so I'm doing that, and then the notary in Morocco is like, "Well, I need to see a birth certificate to make sure you're the dad." So now I have to it's just so much stupid work. I'm like, just believe us, we're not. So I had to send him the birth certificate, scan it, and send it, just to get this passport, so we can go. Mm-hmm. Are you guys watching any TV stuff? There's a lot of good TV.
Good Omens. I
That's so good.
finished it.
Oh, you finished? I haven't finished it. I'm on like the 4th episode.
Yeah. It's
It's so good.
2 days. I'm sad.
It's like
I'm
so.
off
That's a real. There's so much good TV.
I don't watch TV.
Do you watch movies?
I watch movies. Yeah, last time I seen Aladdin. It's really good.
Was it good?
It's very good. You
I should maybe
watch it
see
with your
that.
kids.
But is it as good as the cartoon one? The cartoon one was
Yeah.
so good.
Oh yeah, it's
Cartoon's better.
Because Robin Williams is like so amazing.
no. You'll be surprised.
Really?
I thought it was like he's playing Jin. It's gonna suck.
Well, I mean, I like Will Smith, but I was like, is the genie? I don't know about
Yeah,
that.
He was the
But
best
then-
thing about the movie, I think.
Will Smith?
Yeah, I mean,
He's
it's
very
different.
good. He's very
It's,
funny.
You know, it's different. He did his own
Yeah.
thing. And it
Yeah.
worked.
That's
And then he like
He couldn't do a Robin
changes
Williams impression because that's like
songs
Robin
to,
Williams.
Kind of like his own style. So
Yeah.
it's good.
Okay.
A little more
All like
hip-hop.
iconic songs are there. Though.
Really?
Very
I think
nice.
I'll take my kids to go see it.
I saw this
I'll go see
YouTube
it, too.
video, like it's kind of spoilers, but like YouTube video where it shows like the cartoon version and then
Yeah.
the movie version of like it's the whole world.
Oh, a whole new world?
Yeah,
Yeah.
it looked pretty much the same.
Okay, then I'm gonna. Did you guys see Captain Marvel? I mean, it's already out of the theater,
Yeah.
isn't it? Was it
That one
good?
Was awesome. I saw.
I
it
didn't
in
see it.
the first day.
And I'm sad.
It's okay.
Mm.
Yeah, it's alright. It's like one of those.
Well, the only thing is, I saw Avengers Endgame, and then Captain Marvel's in it, and I was like, well, but it's not. You don't have to see it. It's
Yeah.
not like you have to. But I was like, well,
I kind of
Missed
felt
out.
like I was like, I still don't get like her character, like what she's about.
I don't know anything about it.
But
I mean, like from watching the movie. Like,
Oh, really?
Like I'm not sure what her like if she has a defining
Yeah.
characteristic, but it's weird because she's like. I mean, this is in the beginning, but like she doesn't have her memory of her past.
Okay.
So
She was a human.
Does she ever get it back?
yeah,
Okay.
well, sort of, right?
Well, yeah, technically she was a human, and they did some experience with aliens and stuff, and she got
Because she has all these powers and stuff.
well, yeah, well, she got this like weird experiment on her.
Oh.
She basically become this weapon of destruction,
Okay.
and she's like better than Superman. There's no weakness.
There's no weakness.
Yeah.
That's
Yeah,
what it was like in Avengers. I'm like, geez, it's like
Yeah.
she can do anything. So I figured there was some.
Why don't they call her all the time?
Yeah, that's
Yeah, no, I was like, she's got like all this.
Yeah,
Yeah,
Power
it's
and
like
stuff.
an infinity power stone, even punch her.
Yeah, and it was like she did everything, and then finally got not even killed, just like knocked out or
I
whatever.
just thought it was kind of stupid. Where, like she has no weakness, but still nothing against Thanos. Thanos is like
Thanos
take out
can't.
there.
Yeah, man.
Power still.
Yeah. They got rid of so many people in game. Like Captain America's gone.
Yeah, I'm sad that Tony died. So
Tony Stark died.
Such
Who
a
else
good
died?
tech guy.
Black Widow died, right? Why didn't they have a funeral for Black Widow? That made me mad.
I don't care.
I'm like, you're having a. This is a fictional movie, and I'm like,
Yeah.
yeah, like too many funerals.
Doesn't Black Widow have from a movie coming out?
Yeah, but it's
Yeah.
like
Is it a prequel?
I think it's
Story or something.
not or I think they said it's like just before or after Winter Soldier.
Okay.
Yeah.
I was like, Black Widow. So many people. I guess no more Avengers. What's Avengers gonna be?
The new Spider-Man looks awesome.
New characters.
Yeah.
I think they're gonna do it with the new ones like Black Panther. And
Yeah, Black Panther's really good. Yeah, that makes sense. It'll be
I
fine.
said Black Panther sold a lot.
Black Panther was such a good movie. Anyway, okay. Back to Deadlock today. So, okay. Graph reduction.
What's it ruin our fun?
Sorry. Well, and like, I don't read the comic books, but my husband reads the comic books, so he always knows what's going to happen because they're always ahead, you know? So I kind of like, because I'm like, I don't know what's going to happen. I like that. But, okay. Graph reduction. So, we're going to skip this first part a little bit, do the activity, then go back. Because I think this is going to illustrate it a little better. But the idea is, well, let's talk about this a little bit. Okay. So let's say we have a deadlock. If we take an unblocked process in our resource allocation graph and we remove it, and we keep doing that, we can maybe figure out if there's a deadlock in the system. So a resource allocation graph is completely reducible if at the termination of the graph reduction algorithm all processes have been deleted. So, a state is a deadlock state if and only if the resource graph is not reducible. And then this is saying when you do the reduction, which we'll see how to do it, you can go with like any order. It doesn't matter the order. So let's just see how to do a reduction, and then they're going to give an example of it actually ending in a deadlock state. So we have this state. Here's our resource allocation graph. Processes P1 and P4 aren't blocked because one unit of R1's available. And so it can be basically they can take turns to get this other unit. The remaining processes are all blocked. P2's blocked because it's asking for a unit that it doesn't have. Same for P5. P3's asking for 2. P6 is asking for this one. So, all these are blocked and these aren't blocked. Okay, so we can see that. Now, we're going to see if there's a deadlock in the system. So this is one way to do it. So what you do is you first remove all the processes that aren't blocked. So if we go back to here, right, the processes that aren't blocked are P1 and P2. So we're going to remove them, and we're going to remove all their requests, like all the things they were doing. It's like they don't exist, okay? So at that point, that means because of those two being removed, now P2 and all of their, their allocated resources, they're, not being used, P2 and P5 become unblocked because of that. So we remove those. But even though that happened, P3 and P6 are blocked. And so this graph is called, it's not completely reducible, and we have a deadlock. Okay. So anytime you have like a resource allocation block, what you do, graph, not block, graph, what you do, you start with the unblocked processes, you remove them. Then you just keep doing that, in all their edges. You keep doing that, and if you get to a point where there's processes left and you can't remove them because they're blocked, because you can only remove unblocked ones, then you've got a deadlock. Does that make sense? So like if we think of our classic graph, I need to stop chewing this gum. Like our classic block graph. Let me get this. Where is my, there it is. Okay. E, R, D. Let's see if I can draw this correctly. looks like this. That were blocked. Is there any unblocked process here? We have P1 and P2. Both of these are blocked, right?
Yeah.
So this is a deadlock because we can't remove either one. And when you have something more complicated, then, you know, if you start and then basically you see if you can remove all the processes. Otherwise, if you can't, then you have a deadlock. So, nothing super complicated. Okay. Let's see. Let's look at this activity really quick. And this is just basically reading resource allocation graph to kind of see what's going on. We're going to have to do a little work on one of these. Okay, which process is not blocked in graph A? So let's look at A. Okay, process 1 is asking from something from R3, but R3 is already allocated, so it's blocked. Process 2 is asking for the resource, but it's already allocated, so it's blocked. P3 is asking for this resource. I don't think any of
Everything is blocked, so it's not.
So it's none, yeah. Okay. Which process is not blocked in graph B?
Okay. So
P1 is asking, okay, is asking for this. It's not allocated to anything, so P1's not blocked.
Yeah, so that's not blocked. P1.
Okay. Which process is not blocked in graph C?
P1 is blocked.
P1's asking for the
P2 is
resource that's
not blocked.
allocated. P2 is asking for this, but it's allocated. P3, yeah. Which one did you say, Wika?
P3.
Which graph is completely reducible and thus not a deadlock state? Okay. So we need to work on this. I'm seeing if there's an easy answer.
Is it A? I mean, that looks crazy.
Well, if we take...
I think A is a deadlock.
So it wouldn't be A, because it's completely reducible if it doesn't have a deadlock.
Okay. Right, because you can like follow those arrows and it's just a big circle.
Yeah.
So it's deadlock.
So it's not A. Let's look at B. I mean, do we need to see if there's an easy one? We might have to just draw it. If we took P3, okay, so you have to have at least one that's not blocked to remove it, right?
Yeah, so.
So yeah, this is a deadlock.
Oh, okay.
We're on 4, sorry. Okay, so the first thing we do is we have to find a process that's not blocked to remove it. So this is obviously, there's nothing, these are all blocked. So this is a deadlock. There's a deadlock here from the get-go. Which one here is not blocked? P3, right?
P1. You can take that out, right?
Is P1 blocked? Yeah, P1. So, sorry. So we take P1 out and all of its, I guess we could draw it. I could draw it. Okay. So P1's not blocked, right? Okay, so we have R1, R2, R3. Okay, what's process 2 connected to now?
Sorry.
Sorry, making you go.
What was the question?
P2. So we got rid of process 1.
Mm-hmm.
So was it allocated any of the
It
resources?
is connected to R1, R2.
It was R3, right?
It's got R3 and it's asking for R2.
So it's releasing R3. P2, R1 is going to be allocated to P2. Which one was asking for R3?
We doing B?
Yeah, we're reducing it.
P2 and P3 are asking for R3.
Okay. Is that it? What about this resource? Does anything ask you for this resource?
No, once you remove P1, nothing is.
Okay. What is there something not blocked? None of. Well, this isn't really blocked.
Right.
These aren't blocked here. So, and this is unblocked, right?
Right.
So we could remove either of these. It doesn't matter. So this is reducible. Yay! We did it. Do we see how that works? Should I? Okay. Let's do the last one so we can see what happens. It should be. Have a deadlock event somewhere. Okay. Okay. So. Okay, so we're getting rid of P1, and so R1 isn't going to have anything incoming. Oh wait, that doesn't matter. Oh, P3 isn't, sorry. Right. Okay. So P2, it's our allocated here, and then P2 is requesting R3 still, which is fine. And then R2 is going to be assigned to P3. Am I missing anything? One assigned to P2. Okay. So this one's gone. Oh wait, I need to make sure P1 wasn't blocked. Is P1 blocked? Let's start over. Sorry. I didn't do that. That's our first question. Okay. Which one of these is not blocked? R1, but it's P2. It's asking for R3 that's allocated. P3 is asked R2. P3 is not blocked. So let's get rid of P3. Sorry. I just want to do one. Okay, let's do this.
Then you have a deadlock.
Oh, is that a deadlock as well?
It's a big loop.
Okay.
Are you doing C?
Yeah.
R2 went to R3. Or I mean
Oh,
P3.
yeah, good. Sorry. Okay. P3's gone. P2 went to R3. And then R3 goes to P1. And then what am I missing here? Oh, that's gone. So it's just not being used at all.
And then that's a cycle.
Yeah. It is. These are both blocked. Yeah. Okay. So questions about that? So that's nothing too. Sorry, it's that you weren't here. I waited for you.
It took a lot longer than I thought it would. You just stop it. I was like, I was trying to. I tried my best.
I gotta go.
I was like, I still have class right now.
Okay. Let's see. So
I'm not teaching as well.
let me think what I want to do. Okay, so we're going to talk about this one and then we're going to stop. So I'll just make the test up to this section here. It's the last part of 5.2.
Or with them.
So it's going to be like
What's that?
this part, but not the last section.
Not with continuous deadlock detection.
Not with deadlock detection with single unit resources. Okay. So testing for deadlock can be accomplished more efficiently if done continuously. If the current state is not deadlocked, then the next state can be deadlocked if the operation that caused the transition was a request for a resource and the process P that issued the request is deadlocked in the next state. So basically it's this thing. So if the operation that causes the transition from one state to the other is a request for a resource, there can be a deadlock. Okay. So because of this rule, this is what we're going to do. If the current operation is a request for a resource and the requesting process becomes blocked in the next because of that, then we're going to execute the graph reduction algorithm.
Is like S prime the next state?
Yeah. As a result of like doing the request. Until either the thing that's asking doing the request, a process, is removed, or no unblocked process remains in the graph. So if this is removed, it means there's no deadlock. This means basically there is deadlock. Because if you have a graph with only blocked processes, then that's a deadlock state. So the only difference, the thing we're doing here, we're basically saying we're not checking for a deadlock like at the end, we're checking for a deadlock every time there's a request. That's all that's happening. So anytime a process makes a request, then we're going to say, okay, we're going to do like the graph reduction, on the next day and see if there's a deadlock. And if that process that is making the request can be removed from the graph, then we're saying there's no deadlock. Otherwise, there will be. So let's just look at an example here. So if P is removed, this is the process that's making the request, then the next state, S prime, is not a deadlock state and the algorithm terminates. Okay, so let's do this. Okay, so during continuous deadlock detection, the current state, so this is not a deadlock state. It's just telling us that. There's no deadlock happening here. Now, P1 is going to request R2. P1 becomes blocked, and so at that point, it's a request. It's a request, and so we're going to do a graph reduction to see if there's a deadlock now. Okay, so because of graph reduction, this one's blocked, so we can't remove it, but P6 was not blocked. So let's go back to here. Yeah, P6 is our only unblocked process, so it's removed, and this is just to, that's going to unblock P3 and P5. This is the one that has to be removed, though, for us to continue. So we haven't done that yet. The next step can remove P3 and P5, which unblocks these two. So now when this one can be removed, we're good. So you can stop early, basically. And so the new state's not deadlock, and so it goes into the new state. I mean, something they don't explicitly say, but like, it's only when the process requesting blocks, because if it's not blocked, you could just remove it, and then that's definitely not a deadlock. So let me make a note.
Isn't that what it said though?
Did it? Maybe I just didn't read it good enough. It says deadlocked. I think it means blocked. Unless maybe I'm...
Oh, I see.
So I think that's what they mean.
Like it should just be blocked.
Yeah, I'm gonna say something here. Oh, oops. No, I don't need Safari. Should be. Okay, there we go. Okay, so let's kind of look at this. So we're at the first state. This is our graph allocation thing that we have here. If P1 requests 2 units of R2 instead of only 1, then what will happen? The graph reduction algorithm will remove P1 as before. So if P1 requests 2 of R2, it's going to be blocked because there's nothing there. I mean, there's nothing for it to get. And so, so we'd have to go through this whole thing.
I think it's a deadlock.
If we just looking at it, will be a deadlock. It looks like a deadlock to me.
You'd remove P6, P5, P3, P2 could get removed. But then P1 can't get R2 because there'd only be 1 available.
Right. So the new state will be a deadlock because P1 and P2 jointly request 3 units of R2, but R2 only has 2 units. But it's not. Oh, it means together?
That's wrong.
The new state will be in a deadlock state because P1 cannot be removed. Well, that's the reason.
I think I get what they were saying in that paragraph above the diagram.
This one?
Yeah, they're saying if your current state is not deadlocked, then the next state can be a deadlock state only if you're requesting a resource and it put you in the
I
process
understand.
becomes deadlocked.
Well, that makes sense because it's the new process, so it's going to be the one that causes the deadlock. Okay, that makes sense. But they don't talk about, and I guess it's kind of intuitive that if it's going to cause a deadlock, it has to be blocked. So it's like part of it. Yes. But still, I think they should kind of say it a little better way. Okay. So P1 and P2 are sharing resources R1 and R2. P2 is holding R1. So here we see, this is our resource allocation graph. So the graph reduction algorithm needs to be called when P2 request R2. No, because we only call when something's blocked. It won't be blocked. P2 request R1. What? Oh, releases. Oh, I thought that was request. Sorry. Okay, ignore me. I should have read it more. P1 request R1. That's this one. Sorry. R1 is held by P2 and thus P1 blocks. Okay. So only when it's blocked. Sorry. And then we're stopping there. And we will have this in the next section. I mean in the next test. Let's see if there's anything here we want to do. What's our time? We have 20 minutes. Why don't you, let's just work on 521 just for practice.
Sure.
And so that's using graph reduction, determine if this graph contains a deadlock. 521 is the exercise. I'll make it visible here. See if there's anything else to do here. Okay, so the first thing to do is remove, let's just work it out on the board, actually, is we want to remove a process that's not blocked. Let's stop this.